Let's see, they're asking us to find the equation of the tangent line to the curve of intersection of the surfaces z equals x squared plus y squared, and z equals 4 minus y at the point 2, -1 and 5. Alright, so intersection of surfaces, well, it seems like we will have to calculate a couple of gradients, and well, how about we look at the picture for this. So number one, what do we have? Let's actually treat everything as implicit functions. So number one, so that's which is z equals to 4 minus, well, not actually x squared plus y squared. That's the same as saying big F equals x squared plus y squared minus z. And if we find the gradient, this will be 2x, 2y, and -1, because the derivative of negative z is just 1. Now let's evaluate the gradient at that given point, which in this case, well, nabla f 2, -1, 5. That's 2 times 2, 2 times -1, -1. There's no variables to plug in, so that's going to be 4, -2, -1. So that's the gradient for the first surface for the paraboloid. Now let's get the gradient for the plane. For the plane in this case, so the plane, which is z equals to 4 minus y, and if we create a big function f, an implicit function, that's going to be 4 minus y minus z. Well, actually, let's use a different letter because we already used big F, so let's call it big G, so we don't get confused with the same letter because we already used letter F. So let's find the gradient of G, that is nabla G. That's the derivative of 4, which is, well, actually there's no x, it's actually 0. The derivative with respect to y is -1, and -1 for z. So this one is really easy to differentiate. Well, we want to differentiate to rather evaluate the gradient nabla G at the point 2, -1, 5. But in this case, notice how the gradient in this case it's a constant vector. There's no x, y, and z to plug in those values, so it will be the same components in this case. I know I should have just called it here, but just to be consistent with the notation and the process that we've been following, I'm just going to write this. And well, no wonder the gradient for that given surface is, it's constant because, well, it's a plane, isn't it? So the derivative, the rate of change, it's always the same, So what are we going to do in this case? Because notice in this case, that line it's an orthogonal, In this case, we need to do the cross product between f, that is I, j, and k, for -2, -1, 0, -1, -1, and well, let me actually repeat the first couple of columns.
For cross product, when we have gradients, we don't use the x, we use the dot.
Yes, that's x. Thank you. It's a cross product. Yeah, no, not a dot product. Thank you. So that's a 4 minus 2, 0 minus 1. And well, so doing this cross product, just to save time, this should give us the following vector: 1, 4, -4. Okay? So, again, why are we doing the cross product? Recall that the cross product gives us a vector that is orthogonal to these two vectors, but in this case, these vectors, which are the vectors that are normal to the planes, but for both f and g respectively. Well, in this case, the vector that is normal or orthogonal to those two vectors will be the direction of the line that is tangent to that surface at that given point. So that's why we're finding cross product. This vector will be, just to be more specific, direction vector of the tangent line. And well, I think we have all the information to write down this vector equation. That's simply r of t, and that's 2, -1, 5 plus t, 1, 4, -4. All right, so that's the equation in parametric form. I'm not going to do the IJK this time. All right. So I think this concludes this first part of the section about tangent planes and lines and all that. So now let's look at linear approximations. Well, so we use linear approximations to calculate certain values that we cannot, calculate with the given functions. For example, if we wanted to calculate the square root of 26, well, so in this case we would need to guess a function and find the equation of a tangent line at some point close to at some point x that is the closest perfect square. So we would have to guess the function and then a nice number. So for example, in this case, at a equals 25, we do the equation of the tangent line, we obtain a linear approximation, and then a linear equation which we can use to approximate values, right? Well, we went back to this idea last semester when we covered, remember, Taylor series and Taylor polynomials, how those polynomials are used to give us even better approximations than the linear approximation. So the second degree Taylor polynomial gave us the more terms that we added to the approximation, the better the value and closer to the actual value. We did, well, a bunch of examples on those. Of course, actually, there are this Taylor series and polynomials in two variables, but that's something we're not going to cover in this class. All right. So, well, the analogous here to 3D. Well, so notice how we use a linear approximation, or the equation of a line, to approximate some value. So in the 3D space, we're going to use not the equation of a line to approximate, but we're going to use the equation of the plane to do approximations of values, but in this case for functions of two variables. So we're just adding a couple of terms here and there. Well, so let's recall how we got that linear approximation. So pretty much every function f of x can be approximated to some L of x, so some linear function, and that's equal to f prime evaluated at a, x minus a, plus f of a. In Calc 2, we wrote this in the reverse order. We started with f of a, f prime a times x minus a, and then we were adding more terms. That's a f double prime a, x minus a over 2 factorial plus f triple prime, oh, that's squared actually, of a, x minus a cubed over 3 factorial. Remember those expansions that took forever to do? Well, lucky for us, this time we're not doing anything beyond the linear one. All right, so yes. All right, so how does the linear approximation looks like in two variables? Well, the rate of change with respect to x times x minus a, the rate of change with respect to y times y minus b, plus f of a, that becomes just f of a and b. I mean the function evaluated at the 2 points. That's again the rate of change in the x direction. Well, back in Calc 1 we never talk about the x direction because we were only talking about functions of one single variable, so no need to add fancy language back then. But what's this ultimately? Isn't this the equation of the plane? The explicit version of the equation of the plane? That's nothing really new. I mean, but now the new thing is the application that we're going to do on this equation. So find the linear approximation for the function z equals f of x, y equals 10 minus x squared minus 3y squared at the point 1, 2. Then use it to approximate the function at 1.1, 1.99. Alright, so what do we have to do here? Number one, let's find the partial derivatives, because we need partial derivatives. We need the gradient vector, because that gradient evaluated at a and b. Okay, so that's let me do the gradient. So the gradient, which is nabla f, well actually in this case it's nabla of little f, because we are working with an explicit function, and so that's going to be the derivative with respect to x, that's negative 8x minus 6y on the y component. And if we evaluate this this gradient at the given point 1, 2, well then this is going to be negative 8 times 1 and negative 6 times 2. Giving us negative 8, negative 12. Alright, so that's these two numbers. Again, we're storing these two numbers in this database, if you will, which are going to be the partial with respect to x at the given point and the partial with respect to y at the given point. What's next? Alright, so because we will need to find f of a, b, let's evaluate f of 1, 2. This time they didn't give us the z value. We had to figure it out this time. So that's a 10 minus 4 times 1 squared minus 3 times 2 squared. All we do is plug in that point on the given explicit function this time. And well, simplifying all this should give us a negative 6. So, and yeah, that's minus 10 minus 4. That's 6 and minus 12. Yeah, that's negative 6. Alright, so let's evaluate, or let's get the linear approximation. But this linear approximation is L of x, y. It depends on two variables this time. Alright, so let's see. So that's going to be the derivative evaluated at the derivative with respect to x evaluated at the point, which in this case is negative 8. Well, let me actually write the formulas just so we can relate it. Fx times x minus a plus fy, y minus b, plus f of a comma b, which in this case is, well, that's going to be negative 8 x minus a, which is 1, and minus 12 y minus b, which is 2, and plus the value of z in this case, which is negative 6. That's the equation of the plane that we will use to approximate some values. And of course, recall that we cannot just approximate any value. So coming back to the picture from Calc 1, well, this linear approximation, so it's good enough only to approximate values maybe 24.1, maybe 25. 0.8 for example, but can I use this linear approximation to evaluate or to estimate the square root of, say, 51? Do you see how these two values at 51 are too far apart? In this case, the approximated value from the actual value. So I mean, after certain values of x, these two graphs start to diverge, and that's what is going to give us a really big difference. And so we won't be able to use this approximation to approximate 51. However, maybe if we do an approximation at a equals 49, which is the closest perfect square to 51, well, in that case, we'll have a better approximation. That's one way to fix the issue. Another way to fix it is just to add many terms, but that's a Taylor series, a Taylor polynomial in this case, maybe a 7th degree Taylor polynomial, as many as possible. But well, again, we're not doing that. So the same idea is with this equation of this plane. So that equation of the plane, it's just good enough to find an approximation for this point. Check this out. Do you see how the point 1,1, 1.99 is not too far away from the point 1.2? Yeah, so that's going to give us a somewhat decent approximation. But can I use this approximation to maybe estimate 5 and 7? Maybe not, right? Maybe not. So, all right. So let's see. Also, again, just to, whenever we got this approximation, because it's an approximation, this f of x, it's approximately, well, back in Calc 1 and Calc 2, this f of x was pretty much very well approximation. So in this case, what we're going to do is to say the linear approximation at 1.1, 1.99, that's the same as saying, well, f of 1.1, 1.99. In this case, this is approximately L at 1.1, 1.99. All right, that's so. What do we do from here? Well, let's use that equation of the plane right here and plug in the corresponding value of x, 1.1, and corresponding value of y, 1.99. So this will be L evaluated at 1.1, 1.99. This will be negative 8, 1.1 minus 1, minus 12, 1.99, minus 2, minus 6. Oh my god, I'm glad we're just doing the linear approximation. We're not doing these Taylor polynomials into variables. Otherwise, these calculations would have been big. So 8 times, okay, 1.1 minus 1, that's 0.1, minus 12 times negative 0.1, 1.99 minus 2, and I think it's 0.01, right? And minus 6, and simplifying this we get negative 6.68. Well, in this case, this is the approximated value. The actual value is negative 6.72, which is, I think, a good or a decent approximation. Right? How do we get the actual value? Well, so we're looking for these increments. So number one, okay, first of all, let's go back to the Calc 1 idea. So for the Calc 1 idea, for the actual value, that would have been f of x plus delta x minus f of x. In this case, actual in multivariable would have been f of x plus delta x and comma y plus delta y minus, no, I don't need it, thank you, f of x minus y. Alright, so that's going to be the incremented value minus the original value. That's how we get the actual change. Well, so if we evaluate, so f of, what is this, 1.1 comma 1.99 minus f of 1 comma 2, that should give us negative 6.7. Alright. But we're just going to focus on the approximated values. Yes?
So that is like a decline?
Yeah, so it's just a negative value. In this case, it's not the rate of change. Well, in this case, these rates of change in the different directions are just used to get this change. So it's not that it's in decline or that it's decaying or going up the hill. So it's just an estimation of a value. Increments and differentials. Well, so we got into increments and differentials before getting into integrals, because the integral, it's really the antiderivative of some differential, really. So in this case, let's recall the definition from Calc 1. So given some function y equals f of x, the differential of y, usually denoted dy, it's given by dy equals the derivative of the function times dx. So, and that's because initially we found the derivative of dy dx equals some f prime, the derivative of whatever the function. But I mean, initially we just use that symbol dy dx to denote the derivative or to denote a change of the dependent variable y with respect to the independent variable x. So we really didn't see that as a quotient, but now when it came to looking at differentials, we treated that as a quotient of two quantities, and that's where what we really did is just multiply both sides by the x. And this was the preliminary idea before getting into the integration. But well, not going to do the integrals yet, but we're almost getting there. So let's see. So now in this case, for functions of multiple variables, in this case x and y, which are going to be delta x and delta y. So, and again, in this case, when we did these approximations, we allowed this delta x, this increment, to be equal the x, the differential. And well, what's the picture for this? Well, so back in Calc 1 as well, we got this, we got some function, and it's, well, maybe not here, some function and some equation of a tangent line at one given point. Well, so the equation of the tangent line has the following slope, which it's relating some delta x and some delta y, right? That's the rate of, that's the slope, the rise over run, if you will, the y2 minus y1 over x2 minus x1. However, on the function, well, it's really not that same value. I mean, the delta, the dx, it's pretty close to delta x, while dy, well, notice the difference between the actual dy and the delta x, but that's because it's kind of close to the value. That's why we allowed the x equals to delta x. Well, extending to this idea to functions up to independent variables, well, we already look at this delta z, which is the actual change of the function, f of x plus or minus its increment or decrement, and minus the original function. So that's going to be our actual change. But when it comes to the differential, so the differential this time is going to have a different name. It's going to call the total differential, because for a function of two variables, again, there's a change with respect to x, and there's also a change with respect to y. So we need to include these two derivatives. And well, that's what creates the total differential, because we're including all its derivatives in this case. All right, so, and actually, where is this differential coming from? Remember the chain rule? So in this case, what they did is multiply both sides by dt, and boom, cancel, and that's our differential formula. Again, that's something pretty much coming from that chain rule with one independent variable. And well, there's the two notations, the f subscript and the curly d notation. All right. So, and of course, we can extend this to 3 variables or 4 variables, etc. So let's do a couple of examples and find the total differential for this given functions. Well, so number 1, to find the differential, the z so that's partial z with respect x dx plus partial z with respect to y dy. So we need to find the partial derivative with respect to x. Well, the derivative of x is just 1 times the constant multiple which is cosine. That's going to be cosine y, and then plus the derivative of e to the x y with respect to x. Well, number 1, the derivative of the exponential is itself e to the xy, but what's the derivative of xy with respect to x? Y. Alright, so that's times dx plus the partial derivative with respect to y. In this case, we're going to differentiate cosine. Well, what's the derivative of cosine? Negative sine y times the multiple constant, which is x, that remains there. And well, the derivative of e to the xy is itself e to the xy, but this time times by mini chain rule the derivative of xy with respect to y, which in this case is x, and that times dx. So that's the total differential. So in this case, we are looking at all the changes with respect to x and with respect to y to obtain the total differential. So it's not like back in Calc 1, we just multiply both sides by the x, and that was only one variable. Okay, let's look at the next one. And the next one, oh my god, we might need the quotient rule somewhere. Well, number 1, let's see. So in this case, we have a function of 3 variables. So that's going to be dw will be the partial of w with respect to x times dx plus the partial of w with respect to y dy plus the partial of w with respect to z dz. So we need to find 3 partial derivatives. Well, the derivative with respect to x, well, so what's the derivative of x in this case? Isn't it just 1? All right, now think of the following. Let's split x over z minus 3y plus 4z over z minus 3y. Well, the derivative of this second term will go to 0 because there's no x at all. It's going to be constant. All right. However, here the derivative of x, which is just 1, and this denominator is really a multiple constant, isn't it? We can further see this as x times 1 over z minus 3y. So this is just a multiple constant times the derivative of x, which is just 1. So that's 1 over z minus 3y. That times dx plus. What about the derivative with respect to y? Well, in this case, it seems like we need to rewrite this function the following way. W x plus 4z times z minus 3y, but that to the negative 1. So we will have to use a mini chain rule in here. So to find the derivative, so w with respect to y, number 1, negative 1 in the front. Oops. Yes. Negative 1 times x minus 4z or plus 4z, and z minus 3y to the negative 2, because we subtract 1 to the exponent, but we need to do a mini chain rule here. What's the derivative of this quantity with respect to y? Negative 3. Okay, but negative 3 times the negative 1, isn't that going to become positive 3? And this negative 2 can be sent down to the denominator with positive exponent. So this will be in the first place, so that's x plus 4z times the 3 in the front over z minus 3y quantity squared, and that's going to be our now for the derivative with respect to z. That's the one that will require the quotient rule, because notice how we have z's in both the numerator and the denominator. So let's have a look at this one again. Let's recall what the quotient rule is. So the derivative of u over v, that's u prime v minus v prime u over the denominator v quantity squared. So that's our quotient rule. So, but in this case, we are going to differentiate this given function w with respect to z. So w with respect to z, okay, that's going to be the derivative of the numerator with respect to z, which is just 4 times the denominator, z minus 3y, minus the derivative of the denominator with respect y, that's negative 3, times the numerator without differentiating, x plus 4z, and the whole thing divided by z minus 3y squared. So, well, let's just simplify the numerator. So that's 4z, 4z minus 12y, negative and negative, careful, that becomes a positive, 3x, that's 3x, and that's also positive plus 4z. All right, so let's see how many, oh actually 4z, yes, so that's which one?
If you squared on the y supposed to be both,
Oh yeah, this one?
on
The one above, this one right here? Oh no, because it's only u, not squared. So it would be x minus 4z, and this is just v without squaring.
No, like more up. Like you're missing the parentheses.
This one?
To the right.
Oh, one more parenthesis here, right? Yeah, thank you. And this is squared, so 4z plus 4z, that's 8z. Which one?
Times the x and the 3 plus 14.
So that's negative times a negative, which is positive.
Yeah, that's a 3x, and then the 3 and the 4z can be 12z.
This one?
All the way to the right.
Oh yeah, this one's supposed to be 412z, right? Yes, thank you. And well, cancel. Oh no, that nothing cancels actually. So that's 3x minus 12y plus 16z over z minus 3y squared. So that's going to be our derivative with respect to z. dz. Let me erase all this. So that's our total differential for this weird looking function. Now, how can we apply these differentials? And so you might remember those applications, when you had like a sphere, and when you paint, like one coat of paint to that sphere. I mean, even though this coat of paint is really, really tiny, actually changes the volume of the sphere. Maybe not by a significant value, but that coat actually made an increment in, number one, the radius of the sphere, and consequently made a change in the volume of the sphere. So we're going to do something like that, but before doing that applicated problem, let's do an approximation for this function. Well, use the differential to approximate the change in z as xy moves from the point 1, 1 to the point 1.01, 0.97. Compare the approximation with the exact change in z. All right. So number one, how about we also, okay, well, we're going to do that soon. So let's see, let's find the partial derivative. First of all, find the partial derivative of z with respect x. Well, number one, how about we rewrite the function in rational expression form, rational exponent form. So the derivative will be the exponent, which is 1/2, times 4 minus x squared minus y squared to the 1/2 minus 1. Isn't that negative 1/2? And times the derivative of the quantity inside the parentheses with respect x, which in this case is negative 2x. Of course, we can do some cancellations here. We can cancel the 2's. We can write down that negative exponent in the numerator to the denominator with positive exponent, and again go back to radical. Don't forget about the negative x over the square root of 4 minus x squared minus y squared. So that's the derivative with respect to x. Well, I mean, look at the pattern here. So instead of doing the whole thing for the derivative with respect to y, it's going to be exactly the same, except for when it comes to the chain rule part, we're going to differentiate with respect to y this y squared, so that's going to become a 2y, and the rest is going to be exactly the same process. So how about we just write down that derivative y over the square root of 4 minus x squared minus y squared. Alright, and then we have everything we need to write down that differential. So the differential dz will be the partial derivative of z with respect to x dx plus the partial derivative of z with respect y dy. So this will be dz equals to negative x over the square root of 4 minus x squared minus y squared dx plus negative y over the square root of 4 minus x squared minus y squared times dy. So that's the differential, that's the expression that we will use to find the approximated change. And then we're going to compare with the actual change. So number one, let's see, what else do we need? So so it looks like we need to get the point. Yes. Okay. So z evaluated at the point 1, 1, the z value will be, which is with the value without the increment, that's 4 minus 1 squared minus 1 squared equals to the square root of 4 minus 2, which is the square root of 2. And this value will be used later to compute this value in the denominator for the differential, so we don't have to do it too many times. So in this case, we need to identify dx and dy. So number one, dx equals and dy equals. So notice in this case how we go from the point 1, 1 to 1.01, 0.97. So this means that dx, that is the increment in the x direction, is 0.01. And what would be the increment or the change in the y direction? 0.03. However, it's going to be negative because it's a number smaller than 1. Alright? So yes, in this case the direction matters when it's a larger number, so it's positive 0.01 because it's 0.01 units larger than the initial value. And for the y value, we go from 1 to 0.097, we are subtracting 0.03 units, and we need to include that sign. Alright, so let's evaluate the z, which is, well, negative x, which is 1 over the square root of 4 minus 1 squared minus 1 squared. And what's the x? 0.01 plus negative also 1 because y is 1, square root of 4 minus 1 squared minus 1 squared times the increment, or rather decrement, in the y, in the y direction, which is negative 0.03. And all we have to do is simplify all this. We already did the calculation for the denominator. That's going to give us negative 1 over root of 2 times 0.01. And then plus minus that, or actually careful, because negative times a negative is going to give us a positive, so that still becomes positive. 1 over root of 2 times 0.03. And using a calculator, this is approximately 0.014. Comparing with the actual change. The actual change is 0.0137. Well, compare with the approximated change. I think it's a good approximation, isn't it? So, one more problem. I think it's going to be perfect timing. Well, actually, I wanted to touch base on the next section, at least the first example on max and means, but that's fine. I think we're good with the schedule anyway. So what do we have? The pressure, volume, and temperature of 1 mole of an ideal gas are related by the equation PV equals 8.13 T, where P is measured in kilopascals, V in volume in liters, and T temperature in kelvins. Use differential to approximate the change in the pressure if the volume increases from 12 liters to 12.3 liters and the temperature decreases from 310 Kelvin to 305 Kelvin. Alright, so again, this formula right here comes from PV equals nRT, which is the ideal gas law. But well, in this case, this 8.13 most likely is the computation between the amount of gas and R, which is the universal gas constant. So that's where the 8.13 comes from. Alright, so in this case, well, we want to approximate approximate delta P by using dP in this case. Alright, so what do we have? We have the volume. We have an initial volume going from 12 liters, and we have an increment in the volume. So if it goes from 12 to 12.3, dV has to be 0.3. We also have the temperature, which is 310 Kelvin, and well, since it's cooling because it's still hot, 305 Kelvin, from 310 down to 3.05, so that's going to be an increment, or a decrement rather, of negative 5 units. Alright, again, the sign is going to matter in this case, even though, yes, I mean, in this case we're not taking absolute values as changes. So in this case we go with the sign depending on whether it goes smaller or larger. So let's see. So they're asking us to find the approximate change in the pressure. So that means this formula right here, PV equals 8.13 T, has to be solved for P in this case, which is 8.13 T over V, which is the same as saying 8.13 T V to the negative 1. And this just so it's ready to differentiate. So let's form a differential expression, that is it's not going to be df or dz, x and y, so this time we're going to use different letters. dP That's the partial derivative of the pressure with respect the volume times dV, the increment in the volume, plus the partial derivative of the pressure with respect the temperature times the increment or decrement, depending on the sign. In this particular case, it's a decrement of the denoted dt. Well, let's find the partial derivative. So the partial derivative of the pressure with respect to the volume, that's going to be negative 8.13 Tv to the negative 2 times dV, plus the partial of the pressure with respect to temperature, that's going to be, well, what's the derivative of T in this case? 1 times all these multiple constants, that's the multiple constants. And that times dt. Well, let's write this in a more friendly way. That's a negative 8.13 T over V squared dV plus 8.13 V to the negative 1, actually over V dt. And in this case, well, let's just plug in T and V for the initial values, 12 and 310 respectively. So that's a negative 8.13 times the temperature T, which is 310, over the volume squared, that's 12 squared, times dV, but dV again, that's 0.3, plus 8.13 over the volume, which is 12 liters, just 12, not squared, times dt, which is negative 5. And simplifying all this madness, dP should be negative 8.829. Well, the units in this case, it's kilopascals. All right.